double click on setup, and then you launch Fluent Launcher. We can change this according to the number of CPU cores that you have. So mine was I'll use 16. This is because I can afford 16 cores to perform the simulation. And click start. Make sure you click double precision. And then ANSYS simulation will ANSYS Fluent will start. The layout will look very similar to Fluent meshing. Okay, so you will have your outline view on the left side. So the outline view will be you can just follow this setup from top to bottom. This will be your workflow, and it is also the same when you look here on top. So this is also the same from left to right. So it is very intuitive. You just follow this left side here from top to bottom, which also corresponds to the menu on top from left to right. You will complete your simulation. So for solver type, you will choose pressure based solver, and velocity formulation will be absolute. And this is a steady simulation. So for time, we will select steady. We do not need to take gravity because we are not considering gravitational effects such as buoyancy for this problem. So this is what we start with. Okay, if you click on units, you can change your units, but usually this is already set to default as a unit, so we don't have to change it. So for acceleration is meter over second squared, and we have angle is in degree, area is in meter squared, so we don't have to change anything. We can check our mesh. So when we start here, this is the general settings. We can the scale shouldn't change because we don't have to change this. We will have to deal with scaling if we imported the mesh from another meshing workflow. For example, if you're given a mesh by someone else, and that mesh was created in another software, maybe you need to check the scale to make sure the scale is correct. But in our case, we created the mesh and the geometry in the ANSYS workflow itself. We don't have to worry about the scale. So if we click here, we click check, ANSYS Fluent will perform mesh checking to see if there's any problem, and if there is any problem, it will state here in the console. So basically you have your outline view here, and you have the details here in the task page, and you can see your mesh here, right? So this is this, and then you have a console here where you can see all the information. So what we will do is we will just follow along this workflow outline here on the left side. Okay, so we have already set the general settings, solver type, and the time. So it's a steady simulation. We can go to models. Okay, if we click here models, we have different models. You have multi-phase flow, energy, viscous, your turbulence model, and so on. So since this is a laminar flow, number one, this is single phase flow, only water, so we don't have to check. So we'll turn off the multi-phase model. And then we do not consider energy, the energy equation. We do not have any temperature changes, heat transfer, so we do not turn on the energy equation. And for the viscous model, we double click this. Okay, since this is a laminar flow, we will choose laminar. It means that we do not use any we're not using any turbulence model. Okay, this is a laminar flow. if your flow is turbulent, you have to choose one of the models, and there are many different considerations that you do before you choose these models, because each model is more suitable to be used in different scenarios. Okay, but for this case it's the laminar flow, so we choose laminar and click OK. And then you can look at all these other models that they have, and we do not need to use any of them. So this is done. So we have already chosen the models that we will use. Next will be materials. So by default, Fluent will set the material as air. Okay, if you double click here, you can see at the task page the fluid that we have is air. So we need to change this to water. So we click create and edit, and then you click material type will be fluid, and you have to change. So you have to create click Fluent database and choose liquid water H2O. Okay, the viscosity is 0.001. This is the dynamic viscosity, and then density is 998.2. You can change this if you want, but we don't have to change it right now. Everything looks okay. So we just click copy, and then you can see water liquid here. So click close, and you can click on change or create, and then click close. Now we have water liquid here in our material. We don't need to change anything for the solid one because we don't have any solid. We just ignore this one. We have already add water liquid as one of the materials in our case, but we have not set this material to our fluid itself, to the fluid zone itself. So what we do next is we double click on the cell zone condition, double click on the fluid, okay, and then right here, this is for fluid zone, we have to change our material to water liquid. Okay, so click apply and close. So now we have already applied water to our fluid. Okay, we have already applied water to our fluid zone. So once we have done this, we can delete air. Right click, delete. Because we don't use it, so we don't need to have it here. You don't have to delete it, but let's just delete it so that we don't use it by mistake. So we have already set our materials, and then we have to set our boundary condition. So we'll have, if you click on the boundary condition, we have inlet, which will be the velocity inlet, because this is what we set earlier. And then we have outlet, pressure outlet, and we have wall. Okay, wall we automatically set to no slip. It means there will be no flow, no velocity at the wall. So so let's take a look at our case. Okay, so this is our inlet velocity. So our inlet velocity is 0.01 meter per second. So this is what we will use. This is the value that we will use in Fluent in our setup. Let's go to inlet. If you double click this, okay, we can double click here on the task page. We can double click here on the inlet. It's the same. Okay, you can just play around, try, and see how it changes. Now our inlet will be we will specify the velocity for our inlet. So we'll specify the magnitude, which is in meter per second, and the direction will be normal to the boundary, and the velocity is 0.01 meter per second. This is based on this value, 0.01 meter per second. So it will go normal to the boundary. The direction of the flow will be normal to the boundary. Okay, that is what it means. So let's clear this. So since this is what the boundary looks like, okay, normal to the boundary means that it'll go 90 degrees. Here we go, 90 degrees, normal to the boundary. Okay, this is of course applicable to our case, our pipe case. But you can also decide, if this is not the case, let's say you have a pipe like this, but the flow does not go normal, but it goes in an angle like this. For example, there's an angle, it flows into the pipe with this angle theta, for example. You can determine this angle and this direction here by changing this velocity specification method. You can change it to components, so you can change the x component, y component, z component. You can also change the magnitude and direction using the direction vector. Okay, but for our case, we do not need to do that because the flow will be normal to the boundary. So we will just set the magnitude, velocity magnitude, that is 0.01 meter per second, and the direction will be normal to boundary. So we click apply. So now it is set. Okay, click apply. So this will be the velocity will be applied uniformly on the outlet based on this velocity magnitude. Okay, and then once you have applied, click close. So let's say the inlet velocity profile is not uniform. Let's say at the inlet here, the velocity profile is parabolic, for example. Alright, so let's say this is your pipe, this is the fluid, not the pipe. Let's say this is the fluid, and then at the inlet the velocity has a parabolic profile. Okay, that looks like this, for example. Let's say it looks like this. This is a very rough sketch, but you get the idea. So let's say if this is the case, can we set this up in ANSYS Fluent? The answer is yes. So what we do is, okay, so you have let's just write this down. Parabolic profile, inlet velocity. It means that the velocity changes with the velocity the velocity in the x direction changes with the y direction. Okay, so if you have this kind of profile, you can actually set this up in ANSYS Fluent from the, so double click here, right here, you can set this as expression. We can, or profile, you can use UDF profile, or you can write your expression where you can express this using a formula, using a parabolic formula, and you will have you can set this as a parabolic profile. Although that is not what we are going to do in this lesson, just for your information, it can be done, right? So we are not going to change it. For in our case, we have a uniform profile at the inlet. So next we will go to the outlet. So when we double click here at the outlet, our outlet will be pressure outlet, you can see here, and then for our pressure outlet, the pressure is 0 gauge pressure, 0 Pascal. So we set this as 0 Pascal gauge pressure. And we don't have to change anything else. It means that the gauge pressure is 1 atm. Okay, 1 atm, which is equal to 0 gauge pressure, 0 Pascal. So we click apply and close. And then the last one is the wall boundary condition. We double click here, and this the stationary wall. It's a stationary wall. The wall does not move, and the shear condition is no slip. No slip condition means that there will be no velocity at the velocity is 0 at the wall. Okay, so we don't have to change anything. We click apply and close. So now we have already finished setting up all our boundary conditions. Next, we do not have to change anything else. The reference values, we do not have to change this for this case. We do not have any name expression. So basically we have already finished setting up our simulation. Okay, next we have to set up our solution method. So if we double click on the methods, on the task page you will have this solution method. We have this your pressure velocity coupling scheme, and you have spatial discretization. Because this is a steady simulation, we do not have to deal with time discretization, but this is a pseudo time method. We do not have to change this for now. It does not mean that this is a transient simulation. The pseudo time method means that it will introduce a diffusion term that acts like the time, and it will help with the convergence of the simulation. And that's the very simple explanation of it. So we will not discuss this now. Okay, so let's just keep this as it is, using the default setup. And then when you click on the controls, they are also the same. So we have the solution controls here, where we have this relaxation factor values, and we do not have to change it right now. Just keep it as it is. And then we click on the report definition. We will not do anything for this now, although we will use it later in other simulation. And then this is very important. So we have monitors. If you double click on monitors, we have residual, report files, report plots, and convergence condition. Let's double click on residual. So we'll double click on residual. At the options here, we can print to console. When we check print to console, it means that the values will be printed here on the console. And when we check plot, it means that we will also plot the residual monitors. And let's store the iteration to 1000. Okay, let's perform the simulation up to 1000 plot iteration. And then let's change this criteria to this value. Okay, so basically this criteria will be our residual value. It means that when the residual value goes below this number, the simulation will stop. Or if the simulation goes to 1000 iteration, the simulation will also stop. So it depends if the simulation reaches either this criteria or the other one, or the number of the maximum number of iteration. Whichever comes first, the simulation will stop. So we do this and we click OK. And then we will also double click on calculation activities. So when right here we can set if we want this simulation to auto save itself after a certain number of iterations. For example, let's say we save this data file after every 10 iterations, and let's say we do not retain all the iteration files, we only retain the two most recent files. Okay, we can do this for a steady state simulation, because we do not need to look at the transient nature of the flow. If we do this, what will happen is the simulation will run for many iterations. It means that it will do one calculation and then evaluate the convergence criteria, evaluate the residual values, and then it will perform the next calculation, the next iteration, and then it goes to the next iteration and next iteration. So when we perform autosave, the data will be saved. For example, in this example, it will be saved after 10 iteration, and sysflown will save this data file. And how many files will it save? It will save 2 files. Okay, it means that when you get to the 10 iteration, okay, let's just explain this using write this down. Okay, so when we run the simulation, okay, we will have the calculation will be done iteratively. So it means that you have your iteration, okay, and then you have your residual and other calculation and other parameters. So it will start with the first iteration, second iteration, third iteration, fourth, fifth, sixth, and then the 8th iteration, 9th iteration, 10th iteration. Sorry, 10th iteration. Because we save this data for every 10th iteration, the data at this iteration, and we are only going to save 2 data files. So the data file at the 10th iteration and the data file at the 9th iteration will be saved, and then the simulation will continue. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, and then after the next 10 iteration, it means at the 20th iteration, the data file, sysflown will remove this one and just keep data number 10 and data number 20, because it will only keep the most recent 2 files, file number 1, file number 2, and then the simulation will continue 21, 22, 23 up to number 30th iteration. So when you get to the 30th iteration, sysflown will save data number 30 and remove number 10. It will only save data from the final 2 iterations. Okay, so this is what we set here from the autosave. Why is this important? Because sometimes your simulation will run for days or weeks maybe, and then sometimes you will encounter problems. Maybe the memory of your PC will run out, and then your PC can hang, and if you don't save the data, let's say you will run your simulation for 1 week and you didn't save your data, and after 4 days there's a problem, and your simulation will be forced to stop, and then you don't have any data, you have to restart again. So we start again from 0. So that might happen, that will usually happen. So in order for you to not be able to to be safe, okay, make sure you save your data using the autosave option, and you can set this up according to the free space that you have in your hard disk drive, and also the length of your simulation. So we will save the data files that we will save will be 2, and then we will save the data after every 10 iteration. And let's set this as 5, because I don't think that the simulation will run for that long. Click OK, and then once this is done, we can initialize our simulation. Just choose hybrid initialization and click initialize. When we click initialize, sysflown will assign values to all the parameters, initial values. And this initial values does not have any physical meaning. It's just random value that you put to the parameters to start the simulation, to be able to for the simulation to be able to be run. So once the hybrid initialization is done, it will say it will be stated here in the console, and that's it. We can click here at double click at run calculation. So we do not have to change anything, not now. Okay, but we have to set the number of iterations that we like to run here. So let's run this to 1000 iteration. Now we have this. So we set the number of iteration as to be 1000. It means that the simulation will run to 1000 iterations max. But you also set the residual here, using this value. Okay. So you have these two criteria. Okay, the first one is that we will run the simulation to the maximum number of 1000, but we also run the simulation where the absolute criteria of the residual for continuity for x, y, and z velocity to be 1e negative 6. It means that the residual values will need to, it means that if the residual values go below 1e negative 6, the simulation will stop. And if the simulation reaches the number, the number of iteration for the simulation reaches 1000, it will also stop. So the simulation will stop if it reaches when the criteria reaches either one of these, whichever comes first. So if this comes first, simulation will stop, or if this comes first, the simulation will stop. So this is what we will see once we run the simulation. So we have already finished setting up the simulation. What we can do is we can click, we can check the case. It's good practice to check the case before we run the simulation, and if there is no recommendation that that we can from ANSYS Fluent. So you see here it says no recommendations to make at this time. It means that we can just run the simulation. It means that ANSYS Fluent does not find any problem with the simulation, at least for now. So once we click calculate, ANSYS Fluent will run the simulation. So once we click calculate, you can see in the console here we will have iteration and we have continuity. The values here are the residual values that we set. Okay, since here we set print to console, so this value, the values are printed here at the console. So at the first iteration, this is the residual value for continuity. This is the residual value for x velocity, y velocity, and z velocity. And this is the time that is this time per iteration. So after 5 simulation, okay, see here. You can see here, after 5 iteration, at the 5th iteration, the file is saved. And then this is file number 1 and this is file number 2. So the file is saved at this location, and this is the name of the file, ff1.ces.h5. This is the case file for this project. Okay, and then it will continue to the next iteration, and then it will continue until it reaches the convergence criteria that we set. So this is the residual, you can see. If we look at the folder structure, okay, the folder where we save the file, and when we click here, this is the folder, and then when we click here, dp0 fff fluent, these are the files that is created during the simulation. So you can see here that this is the data file ff1.00005. This is iteration number 5. The data that contains all the information, the velocity, the pressure, and everything else at iteration number 5, and then at iteration number 10, and then at iteration number 15. So it'll only keep 2 files because this is what we set up in the autosave settings. So this is the data file which contains the data at each iteration. It's a .dat file, and this is a case file .cas. So the case file is the file that contains all the other information from the simulation, okay, setup and everything else. So every time we perform a simulation, we need these 2 files, the .cas file or the case file, and the .dat file, which is the data file. And all the other files, msh file is the mesh file that is also in the project. So flprj is the Fluent project file. So these are all the files that will be created once you perform your simulation, and you can find it here. By default, this is how it is structured, and by default this is a name that will be used, fff. So when you look at the workbench, the directory name, you can find the directory name here on the right side. Directory name is fff. You can change it here, I think, if you want to. If you change here, it will change the directory name and the file names, but this is the standard. If you don't change anything, this is what it will usually look like. And if you have many other cases in the same project, it will be renamed to FFF1, FFF2, and so on. So you can, if you do not remember this FFF refers to which case, you can just click on setup or click here and then look at this here, and it will give the name of the directory. Okay. So once we click run simulation, we will have to wait until the simulation ends. Okay, you can see here that residual is going down, and this residual is going down, and then you have to wait until it reaches either 1000 iteration or these values go below 1e-6. When the simulation is done, you can see this notification box. It says calculation complete. So it means that in our case, if we click here on scale residual, it means that you see the number of iteration is 171. Okay, you see in the console here, it says that the solution is converged at the 172nd iteration right here. So the number of iteration did not go to the maximum 1000 that we set, but since the residual value for the continuity and velocity x, y, and z went below 1e-6, the simulation stopped and the simulation has converged. Once the simulation is done, the data will be saved. Okay, writing data and everything, and then you can find this data right here in the Laminar pipe flow files, dp0 fff fluent, and this 170. So this is not the final one, so you have to save. Hold on. okay, you have to save the file. Okay, so how can you save the file? You can go to file, you can save project. If you save project, if you click save project, the project itself will be saved. Okay, when you click save project, the entire project including the workbench project will be saved, everything. So when you look at the folder again, you will see FF100172. So this is the data file at the 172nd iteration. You can also write the you can also export the case and data file. Okay, you can export only the case file, you can export only the data file, or you can export both. So you export, if you export both, you can change the name and then you click OK, and then you export both the case and data file, the .cas and .dat file. Or if you can also export only the case file, or only the data file. It depends. Let's say you have exactly the same simulation, but you want to change some parameters. You want to change the material, or maybe you want to change the velocity inlet, pressure outlet. You can do it by exporting this file, this case file, and then so you don't have to do all the processes all over again. You don't have to start from the beginning. You do not have to create a new CAD model. You don't have to create a new mesh. You can just use this file and just change the velocity profile, inlet velocity profile, for example. Right, but we have already saved the file, we saved the project, so this is the end of the simulation itself. So the simulation is complete.